Good morning. Today we're going to be doing two variable integration, double integrals, and this is going to be we're going to have the midterm, quote unquote midterm, on April 30th. Okay, I'll put it up in the morning, and I'll want you to hand it in the next day, and then we'll have the final on the actual final day. This gives us some time there. But so anyway, on that exam on the 30th will only be two-dimensional integration. So like 15.1, 15.2, and a little bit of 15.4 actually. All right. So again, the triple integrals we'll talk about later. You'll get something on the final about that. But so the stuff I do today will be the last stuff that's on the midterm. All right. I will send out an announcement to that effect. But there you go. All right. So anyway, as I was saying the other day in the Zoom meeting, really the techniques, we don't need to learn anything particularly new here. It's just all the same anti-differentiation stuff. I mean, there are differences obviously from geometry. I'll give you a little heads up here as we go. But again, for the most part, it's really mostly familiar stuff in a new context. Okay. So anyway, let's just get going. So like I said today, that's all we'll talk about is just the two-dimensional integration. And again, we'll talk more about what else it'll be later. Anyway, so just remember the one-dimensional situation. This is easy. You probably even hardly have to say this, but motivates it a little bit, right? So in one dimension, you got the x-axis and then the y-axis for the functions. Anyway, and so just, kind of an arbitrary sort of function there, and remember it's defined geometrically. Say we have limits along the x-axis, say at a and b, then of course the integral, everybody knows this, is the area here, the signed area actually between the curve and the x-axis. So there's our function that we're integrating, y equals f of x, right? And then the symbol, say, is I, something like that. And I'm going to be fairly careful here, because one of the things that gets confusing is actually keeping track of the limits of the different variables and things. So notice how I've actually, the book doesn't do this, but I actually very explicitly pointed out that this limit pertains to x, all right? Anyway, it just helps you not to get confused, right? So the expression, of course, just looks like that, and again, it is just the area there, all right? And of course, geometrically, you make sense of these with these Riemann sums, and I don't really want to spend much time on this at all, right? But, the idea is, once again, there's our function, and so, what you can do is, approximate it by, say, breaking things up into little boxes or something, and so, we'd only kind of keep track of what's in there, all right? And so that's how you actually make sense of these things, and then you use limits, and you make these boxes become infinitely small, and, that's what an integral is. That's really how they're defined from the ground up. Now, of course, just like limits and differentiation, you don't really use them all that much. We'll learn tricks. And in this case, it's anti-differentiation, which is pretty amazing, actually, if you think about it. But anyway, you just have to learn those antiderivatives, and then that's how it works. So here's the geometric definition. But of course, the way you actually work this out is a formula like this one, right? You say, and this is the so-called fundamental theorem of calculus, because it's pretty wild, again, that you define an integration in terms of an area. You define differentiation in terms of a slope of a tangent line. it's really not clear why those two things have anything to do with each other at all. But that's what the fundamental theorem says, right? And it's basically this here is that, you know, if I have a function, say capital F of x like this, happens to obey the anti-differentiation formula that says that the derivative of this new function is the function I'm trying to integrate, then of course we know that the integral that we're calculating actually just comes out to involve only the endpoints, the values of the antiderivative at that function, right? So here's just a really quick kind of summary of there are different things going on. Like I said, the geometry, the analysis here, and ultimately you have to come up with these antiderivatives. All right? Anyway, of course, there's more to integration theory than this. There's a whole bunch of applications and things, but I'm just going to really focus on the anti-differentiation aspects of this, which is what you need to do calculations. Let me grab my water. Okay, so anyway, there you go. So now, really the idea, and again, let me just go ahead and cut to the chase here. See what we're going to do here in 2 dimensions. All right, so for double integrals or 2-dimensional integrals mean the same thing. The main difference is, well, like I say, we're doing it twice as typical. You have to basically do 2 integrals to do 1 integral, and of course the idea is that there's one such integral for each variable. Typically, we'll use the symbol x and y, but you know, there's nothing magical about that. You can use whatever kind of symbols you want. Anyway, and the idea here is now the region of integration now, in 1 dimension, that's just an interval. We integrate from a to b, right? Well, here in 2 dimensions now, it's more complicated than that. And so in particular, say, let's get it up here like this. It's an area that we're integrating over now, not just a length, right? In 1-dimensional integrals, the region of integration is just that interval a to b. Now it's going to actually be a 2-dimensional area within the plane, okay? And the specification of this is really kind of what turns out to be the trickiest thing about all this stuff, but and you know, and it can get hard, but as you know, they say, you just gotta you gotta practice, and eventually it starts to sink in. All right. So anyway, assume that the region is actually a rectangle. Sorry. All right, and we start with a rectangle because it makes everything really pretty simple. We will have to look at more general regions as we go along there, but here's how you start. Okay, so anyway, we're still in 2 dimensions now. But now I'm not going to see the function here, right? I'm only going to see the region. You know, if it's a 2-dimensional function, say z is f of x, y, it's maybe coming out of the board or something. But when we set these guys up, we really just focus on the region primarily. Yeah, there you go. So in this case, then, we'll just have two kind of intervals that we break up, one in x and one in y. So, let's write this out here as, say, R for rectangle. And so, to do this, I now talk about, like I was saying, a two-dimensional region, which we can specify as two intervals. All right, so my x coordinates run from A to B, my y coordinates run from C to D, and you put those together to get one of these two-dimensional setups. All right. Anyway, let me add a little something in here. As we're doing this, then say the points that we're integrating. Say, here we have x, and then, I'm going to make a little area element here that we integrate over, right? So just kind of superimposing that. So again, I go to a point x, and then I'm going to look at a small area element that's just a little bit farther away from x. All right, and the same thing over here, y and y plus delta y. Okay, and so you put all those together and say right here where they come together is our so-called infinitesimal area element, dA, and that's like dx. When you integrate over dx in one dimension, now I'm going to integrate over two things. That'll be the product, dx times dy, as I'll write down here in just a second. But anyway, there's the setup. So in order to do this integral, I eventually have to take all the points in R into an account, which I've specified here. Anyway, and then you look at the value of the function in each of these little area elements. And then what the integral amounts to is doing a continuous summation of all those things. All right, so anyway, let's get some notation for all this. And then anyway, at the end of the day, here's what it looks like. I just put I for integral just so I have a name. It's not important there, okay? So anyway, we actually use two integral signs, it being a double integral. And again, for now, we'll refer to these regions as rectangles R. And so, again, it amounts to, and you integrate over a function, which for the time being, will be in rectangular coordinates f of x, y, and again, my area element is dA. All right, so that's the general notation for a double integral. Now to actually evaluate these things, I need my limits that I had before, right? So the way you actually evaluate this is as two one-dimensional integrals of the type we were just looking at. And there's two ways you can do it at least, and not going to matter here, but in the next section it will. So let me go ahead and get that out. So like I say, we integrate, say, over x from A to B and over y from C to D of some function. And this function actually sometimes is just the number 1 or something like that. It really can be almost anything depending on what you're doing. Okay, so anyway, you could do it like this. And notice how I've done this. This is important. So I've got the x1 out here and the y1 there. And I'm going to keep those together in the same kind of relative order. Okay, so What this says is I'm going to integrate the function f of xy first with respect to y. And while I'm doing that, x is going to be constant. So this is a lot like partial differentiation, actually, right? You differentiate one and you hold the other one constant. Well, this is something like that. And again, you can do it in two orders. This one indicates so-called inner integral, say, here. Just, again, something to call it, which I'll do first. And then the x integral next. Well, of course, you know, what I'm getting at is that there's really nothing particularly special about this. And you can, at least a lot of the time, contemplate doing it in either of these ways. All right? And typically, as I've said about integrals, it can depend on, you know, whether it's easy or whether it's hard, depends a lot on how you set these things up. Okay, so anyway, when we're doing these two-dimensional integrals, there's always kind of two fundamental ways to proceed. And, you know, you'll need some experience in order to be able to figure out which ones you really want to use. All right? And again, the idea here is, and the contrast will be clear in just a minute, the fact that that this region is rectangular is really why I can do it either way, like this. All right? I mean, as we'll see as we go along, and some of you guys I'm sure know this already, there's often more than one way. And, you know, which one can make a big difference. But anyway, just kind of be aware. So really, let's just do a couple of these over some rectangles, because that's really all there is to it. There's not much more to it than this. Again, we'll get to 15.2 in just a second, but let's just go ahead and do a couple of examples of integrals like this, and you should be able to see that it really is pretty much the same thing as what happens in one dimension. Okay, so, right. So anyway, this is number 25 from the back of the book. I don't know if that's one of your homework problems or not. But anyway, like I said, this just shows that this is standard stuff. There won't be anything really new here, except for the fact that there will be two. All right, two integrals to do, like I've been saying. So, say the integral is this. Okay, and this is again, it was set up this way, so let's see, I guess I'm going to do it both ways here. Yes, that doesn't mind. Yeah, so let's say y goes from 2 to 6, and then x maybe goes from 1 to 4. Okay, and then this is, you know, the function that you integrate from a mathematical point of view is not all that important. It can be just about anything, like I was saying. Excuse me. So there's one. All right. Anyway, very easy to do. Well, let me go ahead and just say I could equally well have done this. The same function, but now just the other order. Okay, so again, one of these was in the book. I forget which one, and I'm just doing them here so you can see it. So anyway, there you go. And again, a couple of different ways you can do this, but when you have the rectangles, one of the things about that is you can actually break this up into two completely separate and independent integrals, separate and independent of each other, okay? And that won't be the case in the next section, but that's how it is here. So I could do this, again, a couple different ways. If I want, okay, so if, say, I want to do the y integral first, then I could do it this way. I could say, let's integrate, say, y from, where am I, 2, 6, okay? And then the only thing I have in terms of y is my dy, right? There's no y squared or anything here to put there. So my y integral is just this. That's all there is to it, right? And then this is, you can think of this as the product of two integrals, and then the other integral goes, say, x to the 1 to 4, and now I have to integrate not just over the infinitesimal length element, but the function x squared itself. But now I can just do these integrals on their own. Like I say, they're completely independent of each other. So let me put it below, maybe that'll be a little bit clearer. So anyway, when I integrate this one here, of course I just get the function y, and we have to evaluate that across the limits of 6 and 2. And then over here, this integral just becomes x cubed over 3, and that runs from 1 to 4. Okay, so like I say, nothing new here at all. And easy to evaluate, and of course y from 6 to 2, that just gives me a factor of 4, right? And then this guy here is going to give me, well, 4 cubed is 64, right? Minus 1, all over the 3 from the integration factor, so that's all there is to it. And when you simplify that out, it turns out to be the number 84. All right, so like I said, two completely separate integrals that I, was able to do on the fly like that. It's when you have a rectangle, it's just about that simple. All right, so let's do another one. Rectangle 1 before we look at the more complicated stuff. Okay. This is number 34. This kind of reminds you a little bit of slightly more complicated integration methods. I think I mentioned this. If I didn't, I'll say it again now. That in terms of, I'm not going to give you any really hard integrals to do. That's not the point here. But in terms of what you should know how to do, primarily it's the two techniques of substitution, where you just change the integral into something that's easier to deal with, or integration by parts. All right, I won't ask you to do any trig substitution or anything like that, even though they're not that hard. It's just, again, not what we're focusing on here. So anyway, here's again, it's just from the back of the book. So it's y is 0 to 8. And x goes from 1 to 2, and our function in this case is this one. Okay, and so this has been set up or parameterized. That's another use of the word parameterize here, so that my x integral is my inner integral, the first one I do. If you do it right, you'll get it right either way, but got to be aware of this stuff. Okay? Now, this one's a little more complicated, right? I can't pull apart the x and the y into just two products here. So the form of this integral is a little bit more complicated, not too much, but I can't do it quite the way I did it there. But anyway, so what I'll just do here is like do them one at a time. So let's just go ahead and focus on that inner integral, all right? So that's what I'm going to do here. First, I'll do this integral. Then I'll be left with something that's got no x's anymore, but only y's. And so then I'm left to do the last integral, okay? So again, these are called iteration. These are iterated integrals, okay? And that just means that you first do one, then you do the other. When you eventually get to 3 dimensions, then you've got 3 to worry about. So you do one, then the other, then the last. And don't have to stop at 3, depending on what you're doing, right? Anyway, then, just focus on this, and I'll just mention, quickly that this, I think, is a pretty obvious integral to do with substitution. Okay, and so I won't really beat around the bush. You do have to remember this stuff though. You know, things like well, you'll have formulas, right? So it's a take-home exam, so you really don't have to remember. You know, when I didn't think about that until, you know, here that it is a take-home exam, so I could really give you just about anything I wanted, but I won't. I'll keep it pretty simple. All right, anyway, and so let me just point out here that for the purposes of this integral, of this inner integral that I'm performing right now, y is regarded as a constant. Again, just like partial derivatives. All right. So anyway, here we go, and we make these changes. Then, okay, then what we end up with, the outer integral from 0 to y from 0 to 8 is still there. When I make these changes, I end up with, again, an integral still running from x from 1 to 2. Anyway, when I make these changes, I won't bore you with the details here. You can work it out. Okay, so that's what the inner integral has become. And I'm still left with my dy. That's a very easy integral out there. It is just the square root of 1, or I'm sorry, it's just square root of u rather. So what I'm left with here is integral y equals 0 to 8. And now I simply have that u function there to integrate over, x squared plus, sorry about that. I'm sorry. That's my limit. Sorry about that. And so I'm evaluating that across my limits of 1 to 2. Sorry about that. Now it's correct. And then when I'm done with that, I'll integrate over dy. Okay? So anyway, just working that out again. It's just, yes, sorry about this one. There's my line, sorry. So anyway, yes, let me go here, y equals 0 to 8 again, okay? And then what I'm left with there is simply 2/3, and I got a 4 plus y to the 3/2 power. That's what you get, you know, when you do that one. And then and then I also have, sorry, a little dark in here today, it's hard for me to see. Minus, again, 2/3, and now which is 1 plus y to the 3/2 power. Okay, simplify that out. Let me just put it down here. Can you see it? All right. And the answer comes out to be, again, you can do this stuff. It's a little bit messy, but not too bad. The answer is 16 times the square root of 3 minus 68 divided by 3. Big deal, right? So anyway, there you go. Not a super hard integral, not a trivial integral either, but there you go. All right? Anyway, then that finishes 15.1. I think I'll go ahead and take a short break here, and then I'll come back and do 15.2 in a couple minutes.